Hey guys, I'm back, and this is Josh Myers, and I am bringing you another video on covalent bonding on behalf of Academia on Demand. So as you can see, I have the same setup as we ended with in the last video, and my camera inconveniently decided to screw with me. I use the word screw because I simply do not understand why technology does what it does. Well, I do, but I don't like it. Okay, so what we ended with in the last video was the idea of the net ionic character, net ionic force of a molecule, and how if a molecule is a regular structure and all four groups surrounding the central atom are the same, they have the same electronegativity, so therefore their force pulling the electrons outwards from the central atom is the same, and thus because they separate maximally, they will come to zero when it is a regular structure. However, if we replace one of these groups with a group that is not the same as the other one, so see here we replace the hydrogen with a chlorine which has a higher electronegativity and thus pulls on the electrons more strongly, will create what we call a net ionic force. And a consequence of this net ionic force is that if we take this side of the molecule, we will see that this side, we can label it as having what we call a dipole, and specifically a positive dipole. And more specifically, we would say the carbon has the positive dipole, but just in general, if we're trying to see this idea in a very clear sense, the molecule has separated in terms of what we call dipole. A dipole, which is a partial charge. A dipole. And this is because the chlorine now pulls these electrons more strongly than any of these hydrogens do. And so thus the net ionic force, which would have canceled before, now these electrons are pulled here, so that negative charge is closer to the chlorine. And so now the molecule itself seems to have a partial charge, even though technically it is still a covalent molecule. Okay, and so this has a negative dipole, and so it's almost an 8. It's this symbol. It's almost an 8, and it represents a delta. It represents another way of saying delta, and it represents this idea of dipole, which is a partial charge. It's not a complete ion or anything like that, but it is a partial charge, and this becomes very important in any sort of idea of what we would come to know later as the polarity. Let's erase my diagram on me pushing on the table, because as you see, we have changed tables because my parents are home now and I need a better place to do these videos where they are not getting in my way and I'm not getting in their way. Okay, so now we have this open space here. I've also changed to my green marker because obviously I had to leave the cap off the other one, and it is dried out now. So this idea of these dipoles leads into this idea called polarity. P-O-L-A-R-I-T-Y, polarity. And what this really means is, again, just this idea of charge distribution of a molecule. So charge distribution of a molecule, and specifically when I say charge distribution, I mean charge distribution in a covalent molecule. Charge distribution in molecule. And the reason why this is significant is because this eliminates the idea of any sort of consideration of ionic bonding, of the idea of two ions attracting each other. And it simply focuses on covalent bonding, but where perhaps because of differences in electronegativity, because again, as we see here, this chlorine isn't canceled by the hydrogens because its electronegativity is different. This polarity concept really focuses on this dipole charge. And exactly later on, we will come to understand the significance of this idea in determining intermolecular force. Intermolecular force. And this is the force between molecules. Intermolecular force between molecules. And so here, this molecule, we would say, would be relatively highly polar because due to this chlorine's pull, as I said before, this molecule has a sort of dipole, negative dipole on the chlorine and a positive dipole on the carbon, and therefore the rest of the molecule, even though it still retains its regular structure of 109.5 degrees angles of a tetrahedral structure. So it still retains its regular structure, but now the molecule has a certain partial charge on it. Regular structure. And this is really where drawing Lewis structures starts to become very important, because we come not only to know exactly what they look like, but we come to know properties about them. Because if we can just imagine for a second that this molecule right here was interacting with another molecule, the same molecule, but another one very close to it. Very, very close to it. Okay, hold on. Let's erase this because it's in my way now. Oh no. Hold on. Let's see what we can do. Okay. Alright, we're done. We got it erased. Good. Okay, and then we finally got our last hydrogen. So as we know, this is that partial dipole right here, the partial dipole of the negative and the partial dipole of the positive. And so these molecules, when they interact with each other, will tend to align this partial negative dipole with the partial positive dipole of the carbon and the rest of the molecule, whereas the partial positive dipole of the carbon and the rest of the molecule on this one will align with the chlorine on this one. In this way, these partial charges will attract each other. And this is what I mean when I say force between molecules. These molecules, because of the partial charge, also have a certain degree of attraction between them. And this, as I will explore in later videos, affects many of the physical properties of elements and compounds, such as solubility, such as boiling point, such as melting point, even electrical conductivity to a certain extent. And this is a really, really big concept that we will talk about later. And as you can see, I'm erasing and my table is not very stable. I might have to fix this in the near future, but I will continue for this video. Okay, so we've gotten through this idea of the ionic, of the not ionic, but not polarity idea, the idea of partial charge distribution in a covalent molecule. Okay. So, yeah, and this green marker is really not cooperating. But now we've learned about enough structures that now we are going to make a table and just go over them before we talk about the exceptions, major exceptions and major changes in the way we think about structures in this video. In this video, I hope to be able to wrap up all of the nuances of Lewis structures, so then we can go into this idea called hybridization, which is super cool, and it personally drives me to know more about chemistry. I find this idea particularly fascinating because it explains a lot of the things that we've been assuming so far when we've been using Vesper theory and the Lewis structure rules in order to draw molecules. Oh gosh, and you are going to absolutely think I am Looney Tunes because I just simply am erasing for such a long time, but I'm really trying hard here. I'm going to not use this table after this video because this is simply unacceptable. So much erasing. Maybe I'll just hold that contest I was talking about now, where you just watch me erase and see who can watch the video all the way to the end. So much. I'm sweating. Okay, so we are going to make this table, and what it's going to consist of is we are going to have a general formula for the covalent compound, for the covalent structure based on the number of areas and the type of areas of electron density. And that's how we've classified them when we name them, so that's how we are going to classify them in our table. Alright, so it looks like we are just about done erasing. Alright, that is the really, really tough stuff. We've just finished erasing for the last 2 minutes. Okay, so this table, first thing we are going to label it is the names. The name of the particular molecular structure that we will be discussing. And then we are going to say its general structure. General, G-E-N, structure. General structure. And then let's make a big line here. And then we're going to leave some room. And now we're going to talk about the bond angle. That won't take very long. It's just kind of a memory thing. You just kind of got to know. There's a little bit of logic involved. And then finally, we're going to talk about some examples. And we've already talked about quite a few. But now this is the portion where I'm really going to get some of the exceptions out of the way that I've been discussing thus far. So the first name, we know the linear molecule. So we're talking about a linear molecule. We know that this means there are only 2 areas of electron density around the central atom, if we are talking about a 3-atom molecule, and they repel each other maximally, and thus the molecule is shaped in a straight line. So the one that we talked about in previous videos is carbon dioxide. So CO2. So COO, 2 lone pairs, and then O in 2 lone pairs. And see, now the carbon also has 8 electrons surrounding it. And it has a, oh no, crap. I will have to change that, but this bond angle is 180 degrees. We were going to have to alternate the example and the general structure, because this is an example, it's not the general structure. The general structure will be, let's call the central atom C, and then the surrounding atoms S. And what we will label these areas, we're almost going to star them, because we don't know exactly how the electrons are distributed in any particular linear molecule. What we know is that these 2 exist as areas of electron density that can have single, double, or triple bonds. So single, double, writing sideways is so hard, double, or triple bonds. And so that's where the stars really come in to represent this idea of we're not totally sure, and that's why, by definition, that's what a general formula is. Okay, so now linear. So the next one that we talked about was trigonal planar. Trigonal planar. Not planar, planar. Trigonal planar. And what the general structure that we gave for this type of molecule is the structure of central atom, so C, I don't mean carbon, I mean central atom, and then electron density, S, electron density, S, and electron density, S. Now I don't necessarily mean that all of these surrounding atoms have to be the same. I am simply saying that these S's, which represent surrounding atoms, they all have to be bonded in some way to this carbon, but they don't necessarily have to be the same. They're just simply surrounding the carbon. And then this bond angle is 120 degrees. That bond angle is 120 degrees. And then finally, if we were to give an example, we gave an example earlier of boron trifluoride. So F, and we gave the lone pairs, F, lone pairs, and then F, lone pairs. Okay, and so that is the example that we gave for trigonal planar. And this really, we're just going over this to ensure that we have all of the regular and irregular structures down just fine. And so let's speed it up a little bit here. Now next we've got the tetrahedral. Okay, and so now the the general formula is just going to be, as we predict, 4 S's around a central atom. So S, S, S. Okay, so now the bond angle is, because of the 3D space thing, 109.5 degrees. And I brought a demonstrator today, and as we can see, this 3D space allows us to distribute these atoms in such a way that it's not as though we're taking 360 and dividing by 4. We can actually evenly spread these atoms out in such a way that they are almost exactly 109.5 degrees apart. So I just thought that was interesting because I didn't have that in prior videos. Okay, so now the example we gave before was CH4, so methane. CH4, H, and then H. And so that is what methane looks like. And now the irregular structures, we had the trigonal, pyramidal, the bent tetrahedral, but one that we hadn't talked about yet. Now I'm just going to get into the exceptions because this video is getting rather long, and if you look in the last video you can see all of these exceptions that I'm talking about. The one irregular structure that we actually haven't talked about yet is the bent trigonal planar. This is because simply there was not a proper example that did not involve some exception that I wanted to show you. Okay, so now this example that we are going to be talking about, so I can display this structure to you, is the structure of ozone. And that is that chemical that exists way up in the atmosphere to help protect us as humans from the sun's ultraviolet rays, very high energy rays that tend to make our skin go a little bit on the redder side. Makes us very sad. Me as a red-headed individual, very, very sad. Okay. Good thing I have aloe and sunscreen. Very, very important products in my daily formula for looking wonderful. Okay, so now we are going to talk about ozone. I'm going to talk about ozone. So ozone has the chemical formula of O3. O3. This means that it has 3 oxygens making up the molecule, which means that it has 6 valence electrons per oxygen, 3 oxygens. That's 18 electrons to work with to make this structure. So, as we know, because there's no atom that possesses, lesser amount of atoms in the molecule. There's just simply 3 oxygens. One of the oxygens is going to have to be the central atom. So, as we can simply deduce, it's the easiest way of drawing this is to just simply draw 1 oxygen to start off with. So 1 oxygen in the middle is we are simply arbitrarily declaring one of the oxygens as the central atom. So if we do that, and then we say that each oxygen is bonded to that oxygen by one single bond, Oops, actually I'm assuming something that you don't know yet. Hold on for a second. Let's erase. Let's erase very quickly before it hardens up and it's hard to erase. Okay, Josh is being unprofessional, yes, I know. Okay, so let's redraw this central oxygen and have 1 oxygen bonded single bond and another oxygen bonded single bond. And then with each oxygen possessing 6 electrons that represent lone pairs in its own atomic orbital. Now, how many electrons is that? So, we've got 6 electrons here as lone pairs, 6 electrons here as lone pairs, that is 12. And then finally, each oxygen is bonded by a single bond, so that is 2, 4, so now this represents right here 16 electrons. 16 electrons. So one of the easiest ways to add another set of electrons here is to add a lone pair of electrons. And as we know, this lone pair, because of its ability to repel, tends to shift these bonds downwards below that horizontal plane. And so if we redraw this molecule now we're redrawing with this lone pair, and we have a single bond here, oxygen. And so if we just left it this way now with the lone pairs, I'm not going to draw them yet though, for a very important reason, but let's just assume they had lone pairs. There'd be 6 here, that's 12, and then 14, 16, 18 electrons. Now this would seem as though this structure is fine. We've used our 18 electrons. These two oxygens have full outer energy levels. They have the 6 plus the bond, the molecular orbital. That would be the solid 8. But this central oxygen only has the lone pair and then a single bond on each oxygen, which means it only has 6 valence electrons, 6 electrons in its outermost energy level once you include the molecular orbitals. So how do we get around this problem? Because this isn't like the boron problem where simply the problem isn't solved and we have to accept it as an exception to the general rule of energetic stability. Here, there is a solution. So imagine if we had one of these oxygens, because these oxygens have the capacity, as we see here, to have 6 lone pairs surrounding their bond with the central oxygen. So what if one of these lone pairs decided that they wanted to be bonded to this oxygen too? So what if the structure was like this? And now we will draw these lone pairs. Now this lone pair that was initially would have been right here is now donated itself to be bonded with that oxygen. And this is actually important because it doesn't change the number of electrons in the molecule. The molecule still has 18 electrons, but the important thing is that now the central oxygen has another pair of electrons bonded to it. Now it is energetically stable. Now there's a little bit of a trick here because this example is particularly good to show this idea that this is a bent tetrahedral. It is also good to show this other idea that I will talk about in a second. So the bent tetrahedral, because as we can see here, there are bent trigonal planar. I am just all over the place here. Bent trigonal planar. And this is because there are 3 areas of electron density around the central oxygen. And for this, and this is why it is related to the trigonal planar, which normally just has 3 bonded pairs of electrons around a central atom. Here there is a non-bonded pair, and that's why it is bent. The regular structure has been bent inwards, and that's why it has a bond angle of less than 120 degrees. So less than 120 degrees. Oh, hold on. No, the other, I believe it's this, is less than 120 degrees. Good. All right, good job. Josh, you caught that. So, now, the next part here is to show why this example is also interesting in the form that it has an exception, that it has a detail to its structure that makes it a little bit special. And this detail is called delocalization. And it's a big word, and I'm going to write it out just so you guys can all see. So you can all see delocalization. So it has what we call a delocalization of a molecular orbital. A molecular orbital, and what we will come to know in the hybridization video of pi molecular orbital. Pi molecular orbital. Okay, and so what this means is it is a distribution of a bonded pair of electrons across more than one bond. And this seems extremely obscure, but we will come to understand exactly why this is and what cases that it happens in. What cases that this idea of distribution of electrons happens in. And we're getting into a bit of quantum physics here if we try to explain the deeper nuances of this idea, but let's just look at this for a second. So what if instead of the double bond existing on this oxygen, it existed on the other oxygen? Let's look at that for a second. Because it would seem as though it's just a symmetry. There's no reason for the double bond to exist on one oxygen any more than for it to exist on the other oxygen. And thus, it seems as though they almost have equal energetic stability. And because, and this is where it gets tricky, hold on for a second, let me draw arrows. Because there's no more energetically favorable state, because no more energetically favorable state exists. Energetically favorable state exists. Delocalization occurs. Delocalization occurs. So, because of this idea, this happens. Delocalization occurs, and the way this occurs is that we can see. No, let's leave this. This is a good diagram. Let's erase more down here. And what happens is that the electrons that would take place in double bonding on either one oxygen or the other, they are spread out across both oxygens. And I know this sounds extremely obscure. Like, how could there possibly be a single bond that is spread out across two potential bonds? But I'm here to tell you that it is possible, and it is this thing we go into quantum physics called superposition, called a situation in which electrons, as we've stated in previous videos, are not in just one particular location, where they have this ability to be in a continuous state. And this is more of an idea that Schrödinger came up with. In a continuous state across many bonds. Many bonds. In such a way that both of them seem to bond equally with this central oxygen. And so I have to get going here because this video is going to be the longest one ever. So we've got our central oxygen. As we know, both of these states are equally as energetically stable. There's no more energetically favorable state that exists. So the way that we draw this out, the way that we represent this idea is by drawing out the lone pair again, drawing out these oxygens, but then representing the area between them with this dotted line. And what this represents is that these electrons seem to hover, and they will exist in a state somewhere in this area, with these two states here being the extreme states, being the states where these two electrons are bonded only to these two oxygens, and only the state where this oxygen and this oxygen have the double bond. But really, in reality, these electrons actually hover somewhere in between. And the implications of this idea is that the bond lengths change, because each bond has a length. And if we were to just make a general rule, generally single bonds are longer than double bonds, and triple bonds are shorter than double bonds, which means that as the number of bonds in an area of an electron density increases, the length decreases. And this is symbolic of the strength of triple bonds relative to single bonds. Because as we know, Coulomb's law, the energy in any bond is the inverse of the radius, the inverse of the distance between the two atoms. So the implication of this delocalization is that both of these bond lengths, when these electrons are in this idea of delocalization, this idea of superposition where they are spread out evenly across both bonds, both of these bonds are of equal length and strength. Equal length and thus equal strength. Equal length plus strength. Equal length and strength. And so why this is important for this structure is because this means that here, if there are two electrons that seem to hover in some space between these two bonds, this means that this delocalized bond, this delocalized energy that is built up in this area, means that these oxygens are bonded to each other. These oxygens are bonded to each other in a length, with a length and strength that is halfway between a single bond and a double bond, meaning that it has a stronger bond than it would have if it was just singly bonded, but not quite as strong of a bond as if it was doubly bonded. And so the strength, we could say, is almost strength equals 1.5 times a single bond. This is our area of electron density, and that is a single bond. 1.5 times a single bond. And that's why this is really, really cool, because we get a situation where both bonds, the strength of both bonds are improved by one set of electrons. And so in the next video, we will finally wrap up our covalent theory, bonding theory, and we will talk about more exceptions just like this one, where different than the norm things happen. Alright, see you later, guys.